Functions and related concepts. So in Math 30-1, we're going to study 9 types of functions and transformations of those functions. So to begin with, we're going to spend a little bit of time just getting to know our GDC, or Graphic Display Calculator, and how we're going to use it to graph the functions, and to understand that it's important to choose an appropriate window and to label graphs correctly if we are in fact sketching these out. So let's take, for example, the graph y equals the square root of x, and it's shown using 2 different settings. So the first is the default setting of the calculator. When your calculator is reset, so this x colon, what that gives you is the minimum x value, the maximum x value, and the scale. And minimum y, maximum y scale. Now, when your calculator is reset, this will actually be a 1, but we're using 10 here so that we don't get all of the ticks. So normally you would see like 10 ticks here if that were a 1. And you know, we've got quadrant 1 here, quadrant 2, quadrant III, and QIV, quadrant 4. But our graph is actually only in quadrant 1. And even when the x value is 10, the y value, I mean, think about it, it's a square root, right? The y value is just going to be a little bit over 3. So we don't need to see the whole of the coordinate plane, at least from negative 10 to 10. We don't even need to see all of quadrant 1. So in the second graph, you notice we're going from 0 to 3, and the square root of 3 is 1.7-ish, so we take this 0 to 2, and we go by ones. And in this, we see the shape of the graph, we can see what it's doing, same basic shape as what's over here, but we're kind of, zoomed in on just the appropriate part. So I'll explain why the settings on the right are more appropriate. Well, the graph only exists in quadrant 1. The graph exists only in quadrant 1. By zooming in on only quadrant 1, more of the graph can be examined in detail. So by zooming in on a portion of a portion of quadrant 1 of Q1, more of the graph can be examined in detail. More of the graph can be examined. If the writing's a little awkward, it's because I'm back on the tablet again, and it's been a little while. So we are going to graph the following 9 functions with a graphing display. We just call it a graphic calculator. We're going to choose appropriate window settings. And so if ever you're answering a question where you have to draw a sketch, and that would occur on the written response of your diploma or on the written of an in-class test, then, we may ask you, record the window settings used. Okay, and this is actually on the formula sheet, so you don't have to memorize this. It'll tell you. Draw a sketch of the graph. Label the axes with the appropriate variable. Okay, it's not always x and y. Maybe it's time and height is what we're doing. So the x-axis could be the t-axis, and the y-axis the h-axis. Scale the axes to match the window settings. label the x and y intercepts, asymptotes, and any other important features. Where appropriate, write the equations of all asymptotes, and state the domain and range using appropriate notation. And for a diploma, the appropriate notation is the full write-up of domain and range. So just something to keep in mind. All right, let's do it. Let's start with linear. So let's get our calculator out. Turn it on. I'm actually just going to clear. So second mem or plus 7. Left arrow to all. Hit enter. And 2. So if anything ever happens to your calculator, you lose a list, something, you're not sure, you're getting some error, you don't know how to fix it, just reset your calculator and start over. Okay, so let's go to y equals, and we'll put in x. And, the first time we put a function in, let's just take it to that standard window. So I'm going to go zoom 6 from -10 to 10. And we could say, well, that's really not a bad window for this particular function. I mean, it goes from quadrant 3 all the way up into quadrant 1. Okay, but you can't really cut off 2 and 4. You wouldn't want to just show quadrant 1 or just show quadrant 3. So this is a perfectly valid window, -10 to 10 by 1s, -10 to 10 by 1s. We're going to draw a sketch. Label, this is the x, this is the y. The little arrows on just to indicate that they keep going. Now, in theory, I should be putting 10 ticks. 2, 3, 4, 5, 6, 7, 8, 9. I should put 10 ticks on each of these guys. I'm just going to put some ticks. If you're doing it on a diploma, you might be a little more careful. And let's sketch the graph. We're going to put arrows on because we know that the graph continues in both directions. The domain, linear, set of all x, such that x belongs to the reals. And the range, set of all y, such that y belongs to the reals. And there we go. There's our first graph, the linear graph. All right, let's get quadratic. A try. I'm just going to shift this up and over. Let's go to y equals. We've got the x. Let's just kick over. We'll throw on a squared. Now, we know what quadratics look like, and we've got that full window. So let's just hit graph. We'll take a look at it. And we'll say, well, the full window, well, first of all, it's only in quadrant 1 and 2. We know what a quadratic looks like. We know that we're squaring the x values, so really, 1, 2, like 3 squared will be 9, so maybe we're going to change it. We'll say, let's go from -4 to 4 by 1s. And for our y values, if we want to see, it doesn't hurt to see the axis here. Let's say we go from -2 to 10 by 1s. Let's go adjust that. So I'm just going to hit window. I'm going to change that, -4. Hit enter to 4. Hit enter by 1s. And -2 to 10 by 1. And we'll hit graph. So we are showing a little bit below the axis, even though the curve doesn't go there. This is still a good way to see, hey, look, there's the axis. So let's sketch this out. Let's start with the axis and that. And again, I mean, I should be putting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Should be putting 10 ticks on everywhere. And here just 4. 1, 2, 3, 4. 1, 2, 3, 4. And 3 is 9, so it's going to go about to there. And on this side. Okay, so it's a decent-ish sketch. Domain, set of all x. X belongs to the real numbers. And the range, well, in this case, y is going to be greater than or equal to 0, such that y is greater than or equal to 0. And then we always have to say y is an element of the reals. All right, let's move on. The next one is a cubic graph. Go back to y equals. I'm actually just going to edit this. I'm just going to go up to the 2, change it to a 3. And I'm going to go zoom standard. I don't maybe know what a cubic looks like, so I just want to get an idea in the standard window. Okay. So, well, if we think cubed, right? So 1 cubed is 1, 2 cubed is 8, 3 cubed will be 27, and same thing on the other side. So let's adjust our window. Let's say we go from -4 to 4. So I'll actually go along the same lines as before. And if we're going to 4s, well, we could go to, let's go -50 to +50. Now, if we do that, if we go by 1s, we'll have to put 100 ticks in there. So we don't want to do that. So we'll go by 10s. And let's hit graph. Let's see. Hey, well, it gives us a better idea of what cubics are about, their shape, right? It's not really a, you know, the other part was more zoomed out, and this climbed pretty fast. And this way, you know, because we made that 50, this 3 is going to give us like 27, and 4 would actually give us 64. So we're even closing in on 4, but we don't even have it on the grid. Okay, so let's make note. -4 to 4 by 1s. -50 to 50 by 10s. Okay. So I'm going to sketch that. There's my x. There's my y. Oh, you know what? I mean, it can't hurt to label these guys. Pretend I labeled this. 4. All right, that's going to be 2. That's going to be -2. It's going to be -4. -50. So these, I think, are more important necessarily than me, you know, -40, 30, 20, -10, 0, 10, 20, 30, 40, 50. 1, 2, 3, 4. Okay, and our graph. Now, it's not actually flat in between here. It's climbing the whole time. At 0, it's 0. At 1, it's 1. But, you know, I mean, 1's going to be almost on top. And there. So let's, hang on. Got to get positioned on the tablet so I can try and sketch this reasonably. Okay, I'm reasonably happy with that, and not as happy with that part there, but whatever. That's your cubic. Domain, and the question in domain is always, is there a value of x I can't use? Right? So for a linear, it's just y equals x. We've got x squared, we've got x cubed, right? The times you can't use x's is if they're in a denominator or they're under a radical sign. So in this case, for cubic, any value of x, so the set of all x such that x belongs to the reals. And the range, well, When you cube a negative number, you get a negative number. So this will be set of all y such that y is an element of the reals. Okay, let's move on to the next type of graph, and we will be, looking at all, well, I mean, linears, that was kind of grade 10, right? Quadratics, I think that's all you do in grade 11 is quadratics, if I remember. It's been a while since I've taught the 20 course, but that's all about quadratics. Cubics, something new. Move this guy over so we can do the next one. Radicals. You can say, hey, we just did radicals, right? I could just rewind. We could go back to radicals. So we say 0. You know what? I'm going to go to 16, and I'll go by 2s. And 0, and we only need to go to 4, right, because the square root of 16 is 4. We'll go by 1s. And I'm going to hit graph. And it's best not to do that with cubic. So let's go y equals, and we'll clear that. I'm doing a radical. Second root x. It's like, that's a surprise. And that's not a surprise. That's what we expect. So graphs have their characteristic shapes, right? I mean, think of them as this is the basic radical, right? Y equals x squared is the basic cubic. Where did I go? 0 to 4 by 1s. So 4, 3, 2, 1. And 2, 4, 6, 8, 10, 12, 14, 16. Okay, all nicely labeled. We got 0, 0. The square root of 1 is 1. 2, 3, 4. The square root of 4 is 2. Oh, no, wait. These are 2s. Back up. Okay, hang on. Okay. That's one. Always watch the scale. So here, big lesson, because you never know. I mean, you're doing a question on a test or on the diploma, and you're assuming these are 1s because they almost always are. But no, they're 2s in this case, right? So 2, 4, 6, 8. So look at the labeling. If that's 16, split into 8 parts, then each one is 2. So that's 1. That's 2, 4. 2, 6, 8, so 9 is going to be, 9, 3, and then 16, 4. Okay, so that is graph of a radical. Domain, set of all x. X belongs, nope. Set of all x, oh no. No, there is a restriction here. Set of all x such that x, okay, it's a radical, so whatever's underneath the radical sign, x is greater than or equal to 0, and x belongs to the reals. Set of all y, and the square root of anything must be positive, so the y value must be greater than or equal to 0 as well. And that's radicals. Okay, let's move back over. Rationals, y equals 1 over x. So, you know what, let's just go throw it in and see what happens. Y equals, let's clear this out. Let's say 1 divided by x. Not really sure what this looks like, so let's put in a standard zoom, the negative 10 to 10. And say, okay, that's interesting. And maybe not 100% sure what's happening here, but I'll tell you, well, we sort of know, right? We did that the other day. We know that as these values get really small and 10 to 0, these get really large and they climb the asymptote. And, this is the I was saying radical, isn't I? This is the rational function. So it's the 1 over x, means that we cannot put in a value of x being 0. So there will be an asymptote here, which I can't sketch in on top of the calculator, but I'm going to go -10 to 10. You know, I'll just do the 10s here. That way we only have to put down that one tick. Okay, 10, 0, 10, -10, -10, arrows on all y arrows, x arrows. Okay, sketch in the asymptote. I would change the color, but and let's sketch the graph. So there and there. Equations of the asymptotes. Okay, so this line is the line x equals 0. That is the vertical asymptote. Vertical asymptote, x equals 0. There is also a horizontal asymptote, right? Because you cannot get a y value of 0. No matter how large this gets, remember what's happening as the x values get really large, 1 divided by a really large number is a really small number, but it can never be 0. So we have a horizontal asymptote at y equals 0. Okay, and let's just pull down a smidge so we can get our domain and range. Domain is the set of all x such that x is not equal to 0, but x belongs to the real. So this says all real numbers except for 0. And the range is the same, only it's got y values. So we cannot get a 0 value for y. We cannot make x big enough that y becomes 0. We can get as close to 0 as we want, but you can never be 0. You can never equal 0. Absolute value. Absolutely. So y is equal to, now that's a 20 concept, right? Absolute value graph. So we know it's only positive. Let's go punch it in. So y equals, let's clear this out. Absolute value is in the math menu. It's a math and it's a number function. So number 1 is absolute and it puts the bars in for you. Nice. And we'll go zoom. We'll do a standard window. And we'll say, oh, okay, yeah, standard windows. Okay, but there's nothing down here, right? And let's come in a little tighter on this. So let's say we're going to go -5 to 5 by 1s and -5 to 5 by 1s. So window -5 to 5 by 1s, -5 to 5 by 1s. And, oh, that was, what am I doing? So the y-min does not need to be -5, right? So we can graph it as like -1. Let's change that, -1, just so we will have a little bit below, just so we can see this axis, but we don't need to go down to -5. So 1, 2, 3, 4, 5. That's my x's. 1, 2, 3, 4, 5. 1, 2, 3, 4. And there we go, absolutely. There's nothing you can't take the absolute value of, right? So restrictions are rationals, of course, because you cannot have a 0 in the denominator. And hiding under here are the radicals, because you must your argument to a radical. You can only take a radical of 0 or above, greater than or equal to 0. So domain here is all real numbers. We can find the absolute value, and the range, when you do the absolute value, it's got to be non-negative. So you can't say positive because 0 is not positive and 0 is not negative. So you can say non-negative, which is another way of just saying greater than or equal to 0, right? 0 or positive. That's what a non-negative would be. Okay, 3 more. Sinusoidal. That's half the course. Well, not just sinusoidal. Trig. The trig unit is a good chunk of the course. Okay, so it says calculator in degree mode. So over 2 degrees. And put in the window that's stated. So negative 3, 6, 0. 3, 6, 0 by 90s, 0, negative 1.5 to positive 1.5, and we'll go by ones. We don't have anything to graph yet. Well, we do, but we don't want to, not the absolute value, so let's clear that out, and we will go sine x, and get our very first sinusoidal graph. You will come to know this graph very, 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 very well. Okay, 1, 2, 3, 4. 1, 2, 3, 4. Okay, so a sinusoidal graph does, I don't know what it does. I'm putting some points down so I can actually get a reasonable sketch. Not that I actually drew a reasonable sketch, but so, all right. Anyway, I mean, you've got the graph on there. You'll sketch something out. Something better, no doubt. Domain, set of all x, such that x belongs to the reals. And the range, okay, you do know that sinusoidal has to be between -1 and 1. Okay, what's next? Whatever it is, got asymptotes. The exponential function, y equals 2 to the x, y equals clear to the, okay, so 2 to the power of, the upside down v, there's called a caret, that's to the power of. Let's go zoom 6. Let's see what this exponential looks like. Okay, so exponential 2 to the power up. So you think about it, 2 to the 1 is 2, 2 squared is 4, cubed is 8, and when we get to 4, that's going to be 16. So that's going to go, flying off pretty good. And, on this side, we start going 2 to the -10, right? I mean, negative exponents, we reviewed that. Like 2 to the -10 is 1 over 2 to the +10. Which would be 1 over 1024. So that's going to get pretty small, but you'll never actually get a negative y value, right? You can't make 2 to the power of something come to be negative. So let's go from negative 4, right? That's going to be out there, so we can actually sort of see what's going on a bit, to positive 4. We'll do that by ones. And let's go negative 2, just so we can see under the line. And, 2 to the 4th is 16. So, hey, maybe we go to 20. Let's do that by 2s. So what we're doing is just refining our window, right? I mean, you don't have to go with the first one you try. You try it, you collect some information, and you change. That's how science works. Math works. Math science works. Science math works. Computer science works. All right, that is the shape of the exponential function. We've seen that as exponential growth, something you've literally been exposed to for the last little while. And 2, 20. That's our y. That's our x. 1, 2, 3, 1, 2, 3. This is going to 4, 6, 8, 10, 12, 14, 16, 18. They'll come out nice on yours. Really, when you're drawing a sketch, I wouldn't worry too much about the tick marks unless it's actually a diploma exam, and then you're gonna or a test. So unless it's actually being marked, let's say, at which point you're gonna want to take a little more care, perhaps. So 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 squared is 4. Remember, the scale here is by 2s. 2 cubed is 8. 2, 4, 6, 8. And 16. Okay, and then that's here. On this end, then things start to drop. 2 to the negative 1 is 1 over 2, which is a half, right? When we get down to here, that's 1/16. It's not easy drawing with a pen on a tablet in this. My shoulder hurts too. It's getting stiff or sore. There's no restriction on the domain, right? You can take 2 to the power of anything. You can do 2 to the 0. You can do 2 to negatives. You can do 2 to positives. Range. When you do 2 to the power of something, it has to be greater than 0. So it's a set of all y such that y. So we can't get a 0. We can just get as close as we want. Y is greater than 0, and y is an element of the reals. Asymptote. There is an asymptote line here, right? This is it's a horizontal asymptote. And the equation is y equals 0. Y equals 0. It's the equation of this asymptote line. And remember, an asymptote line is a line that a curve approaches but does not touch. And lastly, the log function. Y is equal to log x. So let's clear this guy out. Clear. Let's go log x. Close that bracket. Let's go zoom standard. Don't know what this log thing is, but okay. Well, you honestly, you don't know what this log thing is, so I'm going to have to help you kind of fill in. We're going to go from -1 to 10 by 1s, and we will take the y's from -1.5 to 1.5 by 0.5. Okay, so just kind of trust me on this one. You don't know about log functions yet. -1 to 10 by 1s, -1.5 to 1.5 by 0.5. And let's hit graph, see what it looks like. All right, that gives us a bit better idea what's going on. So let's sketch this here. We'll bring this out here. Let's call that 10. Let's call that y. That's 1.5, 1.5, -0.5, -1, -1.5. And our graph, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Our graph actually goes through here. It actually comes up like that, and this side goes down, and then this actually does go along here. That actually is a vertical asymptote. That is a vertical asymptote, VA, and it has an equation of x is equal to 0, right? It's just basically the y-axis, which is the line x equals 0. Domain of a log function is the set of all x such that x is greater than 0 and x belongs to the reals. Okay, and we'll be studying each of these functions in much more detail as we go through the course. Okay, so I'm gonna put that away. Go away, and pop over to the next page. I'm going to pause for a sec, not that you'll notice in the real world, but okay, so we've looked at the 9 basic functions, and you'll see them repeated in the tables here. Each table, there's 9 tables below, and you're going to find 27 equations down at the bottom of the next page. But you'll be able to see the 2 pages, I think. So we've got these 27 equations, and what we want to do is go back. Write the equations of each of the 27 functions in the same box as the basic function that shares similar characteristics. So there's 9 boxes, 27 functions. There'll be 3 in each group. Once you have grouped the functions, describe the common characteristics. So basically what I'm going to do is just pause this and write the answers in, and then I'll open up and we'll just go through each one. So you should go through and fill in the table, and I'll meet you back here in a bit. Okay, just going to pop back in for a sec. Okay, so here's the first one done. I'm waving my hand over it on the screen, of course. You can't see that. Here's the first one done. These are the 3 linear functions out of the group of 27, and they are polynomial functions. They're linear. Polynomial of degree 1. Make that a 1. A 1, 1. Okay, so meet you back up in a bit, and we'll look at the 3 quadratics and the 3 cubics, and then we'll just kind of scroll through the rest. Okay, got lazy, opened up the PDF of the answers, and of course all those PDFs are available to you through Schoology. But here we go, I'll fill it in. So let's just take a quick look. Quadratics are all going to have an x squared, right, and nothing else, no higher power. So they're a polynomial of degree 2. Cubics, well, they got an x cubed, that's their characteristic. Polynomials of degree 3. Radical has a radical sign, and what's important is that the x is in the radicand, that the variable you're taking the square root of, and this thing is varying. Rationals, the x is in the denominator. Oops, oh, it all's blue. X is in the denominator's characteristic. Absolute value, the x is in the absolute value sign, right in between the absolute value symbol. Sinusoidal all have a sign. We're doing the sign of. Exponential, the x is in the exponent, right? That's why it's an exponential function. The variable is in the exponent. And logarithmics use the word log, right? It's the log of x. Okay, so that concludes parts A and B of, what's it called? Functions and related concepts.